We're going to do a proof today, and I think you're really going to like it. We're going to prove that every n plus 1 element subset of the numbers 1 through 2n has at least one pair of numbers a, b, such that a divides b. So for example, let's say we have n equals 3. So no matter what 4-element subset of the numbers 1 through 6 we pick, there's going to be a pair of numbers that one divides the other one. So for example, if we had 2, 3, 5, 6 would be our 4-element subset, and clearly 3 divides 6, 2 also divides 6. Okay, so we're going to prove that it's impossible to find an n plus 1 element subset of the numbers 1 through 2n such that no two numbers divide each other. Okay, so if you're able to solve this, let me know in the comments, but this is actually pretty tricky. So our goal is we want to take the set of numbers 1 through 2n, and we're going to express this set as a disjoint union of n subsets that have a certain property. So we want to write it as, let's call it maybe A1, and then we use this notation for disjoint union. It's like the union sign but with a square. A2, disjoint union, AN. So we want to express the set 1 through 2n as a disjoint union, and each of these subsets here have the following property. So if we have two numbers, let's call them I and j, in one of these subsets, we want the property that either I divides j or j divides I. Okay, so we want to express the numbers 1 through 2n as a disjoint union of n subsets with this property. Why do we want to do that? Well, then when we went to create our n plus 1 element subset, the pigeonhole principle would say at least two elements would come from the same a sub k. And then this property holds, which is what we're trying to show. Okay? So how do we do this? Well, maybe we start with the powers of 2. Right? Any two elements in this set, one would divide the other. So if you took 2 and 8, 2 divides 8. If you took 4 and 32, 4 divides 32. Okay? And that's some of the numbers. Well, what's the next number that's not included would be 3. Okay, and we could take every element in this set and multiply it by 3 to give us some new numbers. So maybe 3, 6, 12, 24, and so forth. Okay, and you could see that if you take any two numbers in this set, one of them would divide the other. And we could continue this all the way through. So what's the next number that we haven't included yet? Is 5. So we'd have 5, 10, 20. So what I'm doing is taking this first set and multiplying everything by 5. 40, and so forth. And we can continue this process. Notice the first entry in each of these sets is just the next odd number, right? It's all the odds, and every entry after that is going to be even because of how we picked the first set. So if we do this all the way through to the last set, which would be, oops. What's the last odd number? Would be 2n minus 1. And then I guess it'd be 2 times 2n minus 1 all the way through. Okay, so we expressed the numbers, the set 1 through 2n, as a disjoint union. How many are there? 1, 2. This is the nth odd number. So we expressed the numbers 1 through 2n as a disjoint union of n sets that have this property. So the pigeonhole principle says if we were to take an n plus 1 element subset of 2n, at least two of those numbers will be in the same one of these partition sets is what they would be called. Okay, and so that proves that any n plus 1 element subset of 2n has two numbers that one divides the other one. Pretty neat. I know it seems obvious, but the proof actually was a little bit tricky. Well, let me know what you think, and thanks for watching.